Hello everyone, myself Soumyajit Khan, a student of Department of Chemistry, Bolpur College. Today I am going to present my dissertation topic entitled IR spectroscopy. Now, introduction. IR spectroscopy deals with the infrared region of the EMR spectrum, that is, light having a longer wavelength and a lower frequency than visible light. Infrared spectroscopy generally refers to the analysis of interaction of a molecule with infrared light. IR spectroscopy detects frequency of infrared light that are absorbed by a molecule. And this is the EMR spectrum. Now, Sir Frederick William Herschel can be considered as a father of IR spectroscopy because he first discovered IR radiation in 1800, and this is the picture of William Herschel. Now, the criterion of IR spectroscopy. The main criterion of IR spectroscopy is there must be an oscillation in dipole moment during vibration. The absorption of infrared region causes an excitation of molecule from a lower to higher vibrational level. All the bonds in a molecule are not capable of absorbing infrared energy, but only those bonds which are accompanied by a changing in dipole moment will absorb in the infrared region. Such vibrational transition which are accompanied by a change in the dipole moment of the molecule are called IR active transition. Let us take an example of CO2. CO2 has 4 vibrational degrees of freedom. One is symmetrical stretching, one is asymmetrical stretching, and 2 is symmetrical bending. In between 4 symmetrical stretching modes is IR inactive because there is no change in dipole moment is occurred during this symmetrical stretching. But the other 3 modes are IR active because there must be an oscillation in dipole moment during vibration. Now, the vibrational energy of diatomic molecules for simple harmonic oscillator. The vibrational energy is given that EV equal to V plus half H omega oscillation in joule unit, where omega oscillation is the oscillation frequency and which is represented as 1 by 2 pi root k by mu, where k is the force constant and mu is the reduced mass. And in spectroscopic unit it will be like that. And this is the vibrational energy diagram for SHO. Now, the selection rule for SHO. The selection rule for SHO is del V equal to plus minus 1. Now, the 0 point energy. If we put V equal to 0 in those previous equations, we get E0 equals to half H omega oscillations in joule unit and epsilon 0 equal to half omega bar oscillation in centimeter inverse unit, and this quantity is known as 0 point energy. Now, diatomic molecule can never have zero vibrational energy. Now, what is the implication behind it? The main implication behind it is the diatomic molecule can never have zero vibrational energy and can never be completely at rest relative to each other. 0 point energy depend only on the classical vibrational frequency and hence on the strength of the chemical bond and the atomic masses. The prediction of 0 point energy is the basic difference between the wave mechanical and classical approaches to the molecular vibration. Classical mechanics would find no objection to a molecule possessing no vibrational energy, but wave mechanics insists that it must always vibrate to some extent. Now, the energy difference. If the vibrational transition is occurred from V level to V plus 1 level, then the energy gap will be del E equal to del epsilon equal to omega bar oscillation. That means the vibrational energy gaps will be equispaced. Now, the anharmonic oscillator. Real molecules don't obey exactly the laws of simple harmonic motion. Real bonds, although elastic, are not so homogeneous as to obey Hooke's law. If the bond between atoms is stretched, for instance, there comes a point at which it will break. The molecule dissociates to atoms. Thus, although a small compression and extension, the bond may be taken as perfectly elastic. Based on this, PM modes provide an expression of potential energy executing anharmonic motion. This potential is known as Morse potential and given below, where D is the dissociation energy and A is the constant. And this is the vibrational energy diagram for enharmonic oscillator. And the vibrational energy expression of diotic molecule according to Morse potential will be like that in Joule unit and spectroscopic unit. And what is the selection rule for enharmonic oscillator? The selection rule for enharmonic oscillator will be del V equal to plus minus 1, plus minus 2, plus minus 3 and so on. Now, the application of IR spectroscopy in organic molecule. The main application of IR spectroscopy in organic molecule is to determine the functional group of organic compound and the stretching frequency of bond. Now, the factors affecting vibrational frequency. There are 5 major factors which affects vibrational frequency. There are Fermi resonance, inductive effect, mesomeric effect, hydrogen bonding and bond angle. If we discuss shortly, then the Fermi resonance, we expect one stretching absorption frequency for an isolated CH bond, but in the case of methylene group, 2 absorption occur, which correspond to symmetric and asymmetric vibration. In such cases, asymmetric vibration always occur at a higher wavelength compared to symmetric vibration. Now, electronic effects. Changes in the absorption frequency for a particular group takes place when the substituents in the neighborhood of that particular group are changed. The frequency shifts are due to the electronic effects, which include inductive effect, mesomeric effect and field effect. Now the hydrogen bonding. Hydrogen bonding brings about remarkable downward frequency shifts. Stronger the hydrogen bonding, greater the absorption shifts towards lower wave number than the normal value. 2 types of hydrogen bonds can be readily distinguished in infrared technique. Now, bond angle. Difference in bond angle also lead to the changes in absorption band. Okay, now the stretching frequency chart. Here, this is the stretching frequency chart, and here we get different types of stretching frequency of different type of bonds. Now take some examples. Here 3 compounds are there. We have to arrange these 3 compounds in their stretching frequency order of CO. Now we already know that NO2 has minus R effect, which decreases the electron density on carbonyl carbon. That's why its stretching frequency will be highest and maximum. And for B compound it will be lowest, because O-methoxy group has plus M effect or plus R effect. That's why it increases the electron density of carbonyl carbon. That's why its stretching frequency will be lowest, and the order will be C greater than A greater than B. Next, the problem B. Here, with the help of inductive effect, that is minus I effect, we can easily solve this problem. We already know that minus I effect order of halides will be fluorine greater than chlorine greater than bromine. That's why the stretching frequency order of the compounds will be A greater than B greater than C. Now, take another example. Here 5 compounds are there. With the help of bond angle, we can easily arrange CO stretching frequency. With decrease in bond angle, the S character on CO bond is increased. That's why stretching frequency also increases from right to left. Next, another example where chlorine is present at axial and equatorial. When chlorine is present at equatorial position, then lone pair repulsion takes place between chlorine lone pair and oxygen lone pair. That's why the electron density on oxygen atom will be increased, and it shifts the electron density towards OC bond. That's why its stretching frequency will be highest and higher than axial chlorine, where no repulsive interaction takes place. And last one is, there are 3 compounds, and here we have to calculate OE stretching frequency. Now, for compound B, there is no hydrogen bonding takes place due to steric repulsion of tert-butyl group. So, B has highest OA stretching. But in case of A and C, for A we get intermolecular hydrogen bonding, and for C we get intramolecular hydrogen bonding. And we already know that intermolecular hydrogen bonding is more stronger than intra. That's why OH stretching for intermolecular will be greater than intramolecular. So the order will be B greater than A greater than C. Now the IR spectrum of butane 2-ol. This is the structure of butane 2-ol. Here we get OH stretching, sp3 CH stretching and CO stretching, and this is the IR spectrum diagram for butane 2-ol. Now IR spectrum of acetic acid. This is the structure of acetic acid, and here we get OH stretching, sp3 CH stretching and C11O stretching, and this is the IR spectrum diagram for acetic acid. And we get OH peak at the range 2800 to 3500, and C11O stretching will be found in the range 1700 to 1750, and for sp3 CH stretching will be found in the region of 1300. That's all. This is my acknowledgement, and these are my references. Thank you. Have a nice day.